models, right? So typically what happens is that you are provided with the input sequence S1 dot 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 to Sn. The first thing we're going to do is we're going to embed this sequence, and then we're going to add to that positional encoding. That's the standard way, those transformers work. So first of all, we're going to embed that and then do some positional encoding. So the embedding is V1 up to V2 up to Vn. So those are embedding vectors. Remember what vectors are. And then we also have positional encodings, P1 up to Pn, and then we add the embedding plus the positional encoding, and then that's the first step we're going to do. After we've done this step, then we're going to pass this into an architecture. So the architecture is going to alternate the attention and then feed-forward layers. So we're going to discuss what those are. But just a bit about notation, which now I think we all should understand. We have something called Z0. So Z0 is a matrix, and that matrix has D by N. So we have D by N. We have D rows and columns. So the idea is that the embedding sizes, we are considering them to be D, and the length of the sequence is considered to be Dn. And that's our matrix Z0. We know what a matrix is, right? We've taken that in this course so far, so we know what it is. And now here we have Z0, which is D by N matrix, D rows and N columns. And then we're going to pass that into this architecture, and that architecture is going to be alternation of attention and feed-forward layers. So those are attention layers. So you take Z0, you pass them by an attention layer, and then after that, you pass them to feed-forward layers, and then this process repeats depending on how many layers you have in your transformer. Now, the mathematics behind what those layers are doing, the first thing is for a layer L, right, for some layer L, we are going to compute the matrix of values ZL by taking the matrix of values at L minus 1, so ZL minus 1. Remember, what Z? Z is a matrix of values. It has rows and columns. And then we're going to do an attention of that layer L of the previous value ZL minus 1, and then we're going to add to that a feed-forward operation of the layer L that takes as an input ZL minus 1 and attention L of ZL minus 1, right? So this is the architecture. We're going to be alternating, these attention and feed-forward layers. And then with the alternation of the attention and the feed-forward layers, we're going to be computing the value of the matrix ZL in this form. So it's going to be matrix ZL minus 1 plus an attention of layer L of that matrix ZL minus 1, the previous layer, right? Plus the feed-forward operation on ZL minus 1 and the attention at ZL minus 1. Now notice that this is like a skip kind of connection because we also have, this ZL minus 1 is also attached, right, to the layer N. Now, what are those attention and FFN layers doing, right? So now that we know how we work with matrices, we can define nicely, this attention layer and feed-forward layer. So in terms of the attention layer L, so imagine you have a matrix A that passes through this operation, which we're calling attention at layer L. What we are going to do is we're going to sum over the H equal 1 to H. So this, we call them the number of heads, right? So we're going to sum over the number of heads. And then we're going to do a softmax operation. I will explain what that is. And then we're going to take that matrix A, multiply it by a matrix WQ. So this is the query kind of matrix. Please notice that this is now indexed by the layer and the head, right? So this is WLH, so W for layer L head H, right? And then we multiply that by the matrix A, which is our input, by the WKLH. So this is the keyways for the layer L and the head H, the transpose, right? So now we know what this T means, right? So this T means transpose, right? We know that. So we know how to multiply these matrices together. Remember how you set your dimensions. If you want to multiply matrices together, we have to be careful because we need to make sure that the number of columns, if the first is equal to the number of rows of the second. So we are able to execute this multiplication. And we also know this transpose operator, right? We also already took that. The transpose operator is simply gonna transpose a column and make it a row, or a row and make it a column. And then we are going to multiply that further by A times WV. We call that the value, and that's L and H again, indexed by the layer and the head. And WO indexed by the layer and the head. Now, some people write this in transformers, some people don't, but the idea is that the way you can write this value matrix is as a product of two matrices in order to accelerate computation. So typically that's what's going to happen. So now, irrespective of the reasons of why we chose all these things, which we are going to describe them in separate lectures about transformers and so on. But what I wanted to show you now is that you can easily understand this equation that you see in transformers, right? Because now we have a summation of a number of heads. We understand that. We have a product of matrices. We understand that. And this is another product by two matrices. We understand how to do that. But notice this is transposed, and we know how to do that. Transpose the row, make it a column, and then multiply that as well, with another matrix. Now, please notice maybe the only thing that we did not take is this softmax, right? So what is this softmax? Let's be clear on that. So softmax is like if I give you a vector, if I give you a vector, right? Let's call that vector. It has W1 up to WK, right? So this is a column vector, it has W1 up to WK. And now if I tell you make the softmax of that, right? So softmax of that. So what will happen here is that you will execute this softmax operation component-wise on this vector, right? Component-wise on this vector. And then each value in these components, it will be e to the W1 divided by the summation of e to the wi for I equals 1 to k. That's the first component of the softmax operation on top of a vector. You take e to the first component and divide by the sum of the e's to the power of every component. For the second component, you do the same. You take EW2, and then you divide that by the sum of EWI. And then that would be the second component, and so on up to the kth component. So the kth component will be e to the wk divided by that summation, okay? So that's what the softmax operation is going to do. The softmax operation, you will give it a vector, and then it will execute this e to the power component divided by the sum of all the sum of e of all the components for the whole vector and produce for you a new vector, okay? That's what the softmax operation will do. So the softmax operation, give me a vector, e to the power component divided by the sum of e to the power components, where the sum runs over all the components of the vector. Now, please notice, we already should understand this, right? Because notice that here I'm multiplying a matrix by a matrix. The product of two matrices is a matrix. We took that in the previous lectures, right? And then here, matrix by a matrix, the product of that is a matrix. And you transpose a matrix, you get a matrix. And now we multiply a matrix by transpose of a matrix, which is a matrix. So we multiply that two matrices. So now the result of all this product inside is a matrix. So now we are doing a softmax of a matrix. What does that mean, right? Because I told you what the softmax of a vector is, right? But what is a softmax of a matrix? So now let's say you have a matrix, let's call that V11 up to V1D, right? And then VD1 up to V, DK or something, okay? Okay, so up to V K D, yeah. So I have this matrix, right, which is made by V11 up to V1D, V12 up to V1D, and so on, and this so this should be VK1 up to VKD, right? So because we have a matrix of K rows and D columns. Now, when I'm doing the softmax operation, all I am doing is I'm going to do this softmax operation on every row of this matrix, right? So I'm going to do this softmax operation on every row of this matrix, right? So therefore, this softmax operation will yield another matrix where each row of that matrix is a softmax operation on the original row of the matrix, right? So here you will have the softmax right, of the first row. So this is equal to that. And then here you will have the softmax of the kth row, right? So when you are doing this softmax on the matrix, all you are really doing is you are taking the softmax of every row in that matrix. So softmax of the first row, softmax of the second row, softmax of the third row, and softmax of the kth row. Now remember what the softmax of a vector is. Now we have a row vector and we're doing softmax of that vector. So the softmax of that vector is nothing but E, like every component is E to the power that component divided by the sum of E of all the components. So now the softmax operation of this matrix, because we're doing it like a row wise, what it will be is another matrix of the same size. However, each row is softmaxed. So each row is, its components will be E to the power component of that row divided by sum and so forth. Okay? So now notice that this result here is a matrix, and now you are doing a softmax of a matrix, which means that we're doing softmax, of every row. And we know what softmax of a vector is. So softmax of this vector, it will be EV11, 1 divided by the summation of E, of all those components, right? So V1I, or I equals 1 to D, right? So that would be the first component of the softmax vector. The second will be E V12. So I will take the second component and take the E of that divided by the same summation, and then repeat for all. That would be the softmax of the first row. And then for the second row, third row, up to the kth row. Okay. So now what is cool, right, is from the lectures we have taken, we can already understand kind of, what the attention mechanism is doing, right? And we can also do the same with the feed forward layer. So if I give you a feed forward, if I tell you the operation is FFN, feed forward network, for layer L of a matrix A, what you will be doing is you will be doing a nonlinearity, Lipschitz nonlinearity, like ReLU, for example, or some nonlinearity you are interested in, tangent hyperbolics or whatever. And then you take this matrix A, multiply it by weight W1 for that layer, and multiply the whole result by weight W2 L for that layer. Okay, so now we know how to multiply matrices together, and this nonlinearity will also be executed component-wise. So this is just every component done the linearity with, and then you multiply that by W2. So now we can understand, right, what this transformer is really doing, right? So first we start from an embedding and a positional encoding. We get this V1, P1 and add them together. And then we get for the second input of the sequence V2 plus P2 and Vn plus Pn. That will give me a matrix Z0, which is Rd by n. What did I do here? I put the embedding dimension in the rows. So I have D rows and columns. We understand this notation, right? And then given this Z0, I will alternate, a set of attention and feed forward, attention and feed forward. The attention is given by this equation, right? And the feed forward is given by this equation. And the way you compute ZL, the value at the nth layer, is given by this equation. Nicely, because we've taken this linear algebra course, we can actually understand how to compute these equations. Because this is a matrix product, this is a matrix product transpose, which is another matrix product. Softmax, we explained that that's an operation that's happening row-wise, where for every row you take the softmax of that row, you will get another row where the components is e to the power component divided by the summation, and the second component is e to the power of the second component divided by the summation of e of all the components, and so on. And then you do that for every row in the matrix, and then this is multiplied by another matrix. And we know how to multiply A by WV and by WO, right? We need to be careful about the sizes. And then the feed forward layer is another thing which is easy. Now we understand how to do. We multiply A by W1 and also by W2. And then we have this nonlinearity that we put in here. Okay. So we fully understand that. And that's really what these transformer operations are actually kind of looking into and they are doing. Okay. Uh, right. Now, please notice, right, that these matrices we introduced, this WQ, WK, WV, WO, W1, W2, right? All these matrices we have introduced in this architecture, we don't know them, right? Like we don't know them. We need to fit them. We need to find them based on the data, right? So we don't know those matrices, right? But we're gonna start with something random, so to say, and then we're gonna update those matrices to better fit my data. That's what machine learning is doing, right? So you start with your architecture and you say, I believe that's a good architecture for me. And then you say, okay, that's a good architecture for me, but I don't know, the weights of this architecture, the parameters for this architecture. And now you give me data, and then I'm going to start playing with my weights, right, in order to satisfy and make you happy with your data. Okay. Right. So this is the attention. This is the feed forward. We spoke about this. And now, after we've done that, then the way this autoregressive operation happens is that on the output of the transformer, you will get a probability vector. And from that probability vector, you will sample the next token and then, add the next token to the input sequence and then repeat, right? So this is how this autoregressively thingy works, right? So you start with the sequence, you do the embedding, you alternate the attention feed forward, as we said with our equations. On the output, you get, this on the output, you get this probability vector from which you can sample the next token. You add that and then repeat. Okay. Now, this is the LLM inside routine, right? This is the transformer, right? We just described. Now, please notice, as we just said, that all these matrices, W1, W2, WQ, WK, WV, WO, for all the heads and for all the layers, they are unknowns. We don't know them, right? It's just this is what we think is a good architecture, that will describe a sequence, right? This is what we are thinking. But in reality, we don't know those values. And now what we're going to do is we're going to try to fit those values depending on my data. So these parameters are parameters of the model. And yeah, the number of those parameters are billions or trillions. Like we have a lot of them. Okay. So now, in order to find those parameters, right, what we are going to do is we are going to define a FTR, which is like a loss function that we're going to then minimize in order to fit those parameters. So the idea here is that if we are provided with a training data set DTR, so detraining, we're going to construct the following loss function. The following loss function is like this. We're going to be sampling sequences and S and Y. So my DTR is made of sequences and Y, sequences and Y, sequences and Ys, right? So it's made of S and Y, S and Y, S and Y. So one sequence and its corresponding sequence Y, another sequence and its corresponding sequence Y, right? And now what we're going to do is we're going to sample S and Y, coming from my training data set. And now I'm going to use my model, okay, PWLLM. So that's my model, right? I'm going to use my model where I'm going to generate the next token conditioned on the sequence and the previous tokens, right? And I'm going to try to find those weights that will make this log P happy. So the idea is that this log P, as we will take later, so that's why you need to continue watching the course, it will be like a maximum likelihood estimator, right? But the idea for now is that this is a loss function that's telling me how probable I am to get the token YT, the token YT conditioned on the input sequence S and the history of the tokens I sampled so far. So let's repeat that. Remember what we do here, right? So we said, okay, we're going to do embedding positional encoding. Then we're going to alternate attention feed forward, right? And then towards the end, we are going to have this probability vector, right? And now from this probability vector, I can sample a token, right? So this is a probability vector over all the tokens. I can sample a token and then I can append it and then I can repeat. right? And that's how I auto-regressively generate. So now next time I'm generating, I will input not only my input sequence, right, which is S, but also the tokens that I have generated so far. So I'm going to input those, and then I'm going to generate the next token. So here what we are showing is that, okay, Y1 up to YT minus 1 are kind of the things, we have so far. And now conditioned on S and Y1 to YT minus 1, I'm going to generate YT, right? And now I want to find those weights such that I can make the probability of getting the YT from my data high. So I'm going to maximize that likelihood. So the weights here, as we said, those are unknown weights, W1, W2, W for all the layers, and the key, query, and value matrices for all the layers and all the heads. And of course, the Y here is just Y1, it's just a sequence. And now the goal is to actually optimize this loss with respect to with respect to those W weights. So the idea is we started with weights which we don't know, and now we are given this training data set detraining. And then what we are going to do from this detraining is to try to fit the weights that will make me do well on my training data set, where do well is defined in terms of the maximum likelihood estimator. Now, to do that, we just typically have an optimization algorithm, which will take my training data and construct a loss function like this and a set of hyperparameters, right? And then it will optimize. So these are hyperparameters, and then it will optimize. So you could use something like stochastic gradient. We will discuss those when we take the calculus part. And then the hyperparameters here will be like a batch size and a learning rate. You can do Adam, which we have a complete lecture on that I will link in the comments below. And also we will take more about this when we go into calculus. And then here Adam will have, more hyperparameters like regularization constants, learning rate, beta 1, beta 2, and so forth. But now with this, what you are able to do is now you are able to kind of, get this W star, and then you evaluate that W star and see how many mistakes you are doing. Okay, this is your test error, where what we do is we sum over a test data set, and we have this indicator of my true Y and my Y predicted, and then I will just measure how many mistakes I am actually doing. Okay. And now, of course, there are many measures for this. This is just one measure with the indicator. Some people are measuring distances and so on, but this is not really of importance to us. What is important to us at this stage in this lecture is just that the concept that we have done so far in linear algebra will allow us to understand the mathematics of the transformers, such as what we show here on how you compute an attention layer. We know how to multiply matrices. We know how to do transpose of matrices. We know how to multiply matrices again. We know how to do now a softmax operator on the matrices, which is row-wise, and we know what we do for every component in that row. We also know what a feed-forward layer is, which is this nonlinearity AW1 of that layer multiplied by W2. And then we said, so now we understand all this, but then we said that, okay, we don't know all these weights and we're going to optimize them. That's why the second part of the math talks will talk about calculus. And then it'll tell us how we optimize these types of loss functions, which I show you an example of here. This will become clearer, in the second part of the talk. So no need to worry about it, a lot now. I will refer to this slide later in some lectures. And also why we use this loss function that needs some probabilistic thinking, which we also will do. Okay, so now I'm excited to let you know that now you are able to do a bit of transformer mathematics through this linear algebra that we have taken. So with that, I would like to end, and I hope you enjoyed this very short note on transformers. Next, we're going to continue with one more lecture about linear algebra, and then we're going to go to calculus and then to probability. All right, so mathematics is not boring. It's actually used in this transformer architecture as we've shown here, and I hope you find this enjoyable. If you did, please subscribe and like the video. Thank you.